Hyderabad as a speaker for this session, and thank you so much, Professor Subramaniam, for accepting our invitation and spare some valuable time for this session. And I hope your lecture will be very fruitful and beneficial for the participants. I also welcome all the participants in this session. Thank you once again, and over to Professor Satan for further proceeding.
Thank you, Dr. Jakhed, for extending a warm welcome to the honorable speaker and to all the participants. Thank you so much. May I now request Dr. H.D. Chalak to kindly do the honor of introducing the speaker to the participants.
Yeah,
Dr.
thank
Chalak,
you, sir.
Please.
Yeah, thank you, sir. Thank you very much. It is my privilege to introduce the eminent personality which is accepted to be an expert of the session. The expert is a well-known academician and a very good researcher. We are having with us Professor KVL Subramaniam from Department of Civil Engineering of IIT Hyderabad, who will deliver a talk on topic innovations in concrete construction for sustainable development of infrastructure. The expert has completed bachelor degree in civil engineering from IIT Delhi in 1993, the master's degree from Civil Engineering University of Toledo, USA in 1995, and PhD in Civil Engineering from Northwestern University, USA 1999. Before joining IIT Hyderabad in 2010, he has worked as a faculty member in City College, City University, New York from 2000. He has also worked in NSF Center for Advanced Cement-Based Materials, Northwestern University, USA. His primary area of working is concrete. Currently, he is focusing on use of paper tubes in construction of lightweight structures, evolution and development of stay-in-place formwork for rapid construction, jointless slabs for use in industrial floors and high-speed trains using fibers. He has 91 research articles published in international journals and 3 research articles published in national journals. Also having 45 research articles in various proceedings of the international conferences. He has 2 book chapters published while addressing 14 gatherings, being an expert in the area. He has completed 13 research projects outside India and 3 research projects in India. Currently working on 3 more research projects funded by government agencies casting in Curves. He received a number of awards and recognitions. A few of them are James Instrument Award by ACI in 1999, Early Career Award by National Science Foundation USA in 2003, ASCE Faculty Award, City College of New York in 2003, Outstanding Young Research Award by GRU School of Engineering in 2006, Teaching Excellence Award by IIT Hyderabad in 2010. He has guided a number of PhD and MTech students and providing guidance for postdoctoral fellows also. He is working as a member of review panel and a member of editorial boards of various journals like Cement and Concrete Composites, Journal of Materials in Civil Engineering, Journal of Bridge Engineering, International Journal of Computational Methods in Engineering Science and Mechanics, Chairman Engineering Panel Professional Staff Congress, Convener Award Committee Indian Concrete Institute. So on the behalf of NIT Kurukshetra as well as EC Bikaner, I welcome you once again, sir, and I hand over the proceeding to Satan, sir.
Thank you, Dr. Chalak. Thank you so much. In fact, and whatever is said about Professor Subramaniam, I carry even more wonderful impression of him. I had the opportunity to interact with him during some faculty selection at certain institute. So since then, I was thinking to connect somehow for some academic activity to Professor Subramaniam to NIT, but then we thought, this is the right occasion. We could catch hold of him and we could request him for, his expertise to be shared with the participants. So my impression stands absolutely wonderful about Professor Subramaniam. I'm very sure all the participants will have really a very good talk and very fruitful for your academics. Maybe you can pick up some threads out of this discussion for your research, or whichever way you can make use of it. So thank you, Professor Subramaniam, once more. I welcome you And over to you, sir, for your session. You may start your session now. Thank you so much.
Sure. Thank you, Dr. Sathans. Thank you, the organizers of this workshop, of this faculty training program under TICIP. So I think I'm really looking forward to this presentation. The topic is very apt on sustainable sustainability in general. I think it encompasses a very broad topic. It encompasses a lot of things. What I hope to put in perspective is what we are doing in relation to construction, and where does concrete fit into this whole sustainability as we're talking about. So hopefully by the end of the lecture, I'll have created an impression about the need for sustainable construction and where the role that concrete can play in sustainable construction. So with that, I am going to turn off my video just to save on the bandwidth. So I'll just share my screen. Hopefully that will go through. Yeah, so my screen should be showing now. I'm in the presentation.
Yeah, we can see,
mode.
sir. It's okay.
Yeah. So now, basically, so welcome to everyone on this to this talk on concrete innovations. I kind of did shorten the title a little bit, made it a little bit catchier. It's concrete innovations, and no pun intended. We do need innovations which are concrete for sustainable construction. So moving forward, okay. Yeah. So what is this material? This people probably don't realize, and I realize I'm addressing a very diverse gathering probably. That is, concrete is one of the most widely used material in the world, and it is second in terms of volume or mass, if you take it, in terms of usage as a material, and it's second only to water. Now, just to put things in perspective, we use about 2 tons of concrete per year for every human being on this planet. So that is the magnitude of usage of this material. So if we are talking sustainable, we have to then address this material. It is the proverbial 800-pound gorilla in the room. So now, what is concrete made up of? Concrete is made up of cement. Cement is the most critical ingredient for making concrete. And what I'm showing you here is a graph that talks about the cement production, past, present, and future. If you look at the different countries and production of cement, the y-axis of the graph shows the gigatons of cement that are produced or required in the future. So if you look at this, basically the red is, of course, the red Chinese dragon. They've gone through their development, and you see that their cement consumption picked up from about 1990s onwards. It's kind of by 2020 they have peaked. The blue in the graph is India, and our consumption is just picking up, and that's because we are sitting on the cusp of development. We're talking about investment of $2 trillion in our infrastructure, and infrastructure cannot be developed if we do not produce enough concrete, and concrete cannot be made without cement. So in India, looking forward, by 2050, we are talking about becoming the largest cement producer in the world just to sustain our infrastructure need. Now, even today, we are second only to China. In fact, the production of cement in India is much larger than all the other developed countries put together, even today. So going forward, it's only going to get worse. Now, what are the challenges with cement production? Cement, basically, just to put things in perspective, we are talking about 750 million tons per annum in 2050. This is, of course, a projection going forward. And that is the kind of demand, or that is the kind of material production we are looking at in order to sustain our needs. Now, where are the challenges with this? Well, cement requires limestone, and the current available limestone reserves are expected to last for another 35 to 40 years. So we may very well use up all our limestone reserves even before we hit our peak production requirement. So that is a major, major challenge, which means, of course, that we have to look at innovative ways of making cement using second grade limestone or looking for alternate sources. for making cement. The other big problem with cement, of course, is that it is an energy-intensive material. It requires a lot of energy to make cement. So we need to look at energy sources. If we are going to continue to make cement, we need a lot of energy to sustain that. Then the last issue and the biggest problem with cement is the carbon footprint. Production of cement is associated with a very large carbon footprint. So we're talking about numbers vary, but even the most efficient cement production plants, we're looking at 1 ton of cement net, if you consider the total carbon footprint analysis, producing about 850 kilograms of carbon dioxide. So basically, it has a very large carbon footprint. So what are the other challenges that we face in construction? Now, most of us are used to seeing concrete construction around us. And we know that most of the beams and columns that we use in construction are rectilinear in shape. So, and that is not the most efficient form that's available. Probably the most efficient form that maybe can be used in construction would be an I shape or a T shape cross section, which is the most efficient in terms of structural efficiency. But with concrete, it is not very easy to do. So when we are talking about making concrete on site, typically we are stuck with forming rectangular or rectilinear shapes. Now, perhaps if I did geometric optimization of the structure in order to minimize the use of material, I may end up with shapes as I'm showing here. Now, doing this on site is just not possible. So basically, which means that the way we make concrete, the way we place concrete, that has to change. We need to look at technology to be able to deliver shapes, and the ultimate paradigm would be to go with form-free construction, which means I am not limited by what I can form using these traditional formwork on site. I should be able to go and freely print concrete. So that is the new direction that all of us, most of us are excited, and we are working in that direction. The big advantage I say as again over there is efficient construction. So what makes this sustainable is, on the one hand, I can basically reduce the material usage and use material more efficiently, more effectively, and that basically will end up in lower consumption of the material, which basically builds towards sustainability. So then the other issue with the concrete construction is it is a slower form of construction. We place concrete in formwork. The concrete slowly hardens over time, and then we remove the formwork. The whole process takes anywhere from 1 week to about 28 days. So, and the biggest challenge that we face with concrete is we're limited by forms that can be, or the shapes that can be formed on site. So, which of course then means that we are looking at formwork which is rectilinear or has sharp corners. The formwork cycle time, assembly of formwork, disassembly, all of these are time-consuming operations. And as we are moving into a new decade and into new era, we would like our concrete technology, concrete construction to be much faster. So that's the other challenge that we're facing when it comes to concrete as a construction material. So what are the solutions now? So we know we need alternate materials. So the solutions lie in the form, 4 of these solutions are what I've listed here. There are, of course, several more, but these are ones that are being actively pursued. The first thing is that now we know the problems with cement. The major thrust is producing alternate cements. We need to look at cements which basically can be made with alternate materials, because I mentioned that limestone, which is one of the raw materials for cement, is running out. We are looking at efficient use of cement. So it's not just that we try to make cement using alternate materials, but try to use cement as efficiently as possible in making concrete. And so that is what I meant by saying the low clinker factor is basically reducing the cement content to produce concretes which are more efficient, deliver the performance with lower usage of cement. Then there is a big push for developing alternate clinker-free binders, and clinker-free binders would be basically concrete which is made using without using Portland cement or without using cement. So there are alternate cements that are being developed, which basically utilize waste materials and basically cut down the requirement of cement either partially or completely. So these are on the cement front, the material front. A lot of research is going on in this domain. The second thing we are looking at is alternate reinforcement. Whenever we're talking about concrete structures, we have to reinforce the concrete structures with steel. And oftentimes the delay in construction is often with the placement of steel. And also steel itself is an energy intensive material. So we're looking at the alternate reinforcement that can come into reinforced concrete structures. The third domain is efficient construction. Can we actually reduce the labor intensive processes? A lot of concrete construction is very labor intensive. So basically try to cut down on the labor requirement, bring in more mechanization, which of course would increase the efficiency of construction. And we are, of course, as I had mentioned, talking about form-free construction, and that is not to be limited by what I can form on the site. So forming on the site would mean that I'm limited by whatever form work I can assemble and the shapes I can deliver on site. So is it possible that I can now think about 3D printing? And finally, of course, this is another big issue, big topic when we're talking sustainable development, is managing energy demand. There, of course, we have become in India and most developing countries, as we become affluent, our biggest energy consumption goes into cooling or heating, depending on the geographical location. And in India, if I particularly talk about India, slowly our energy bill, or what we're paying for energy for cooling, has been increasing to the point that the energy demand required for providing thermal comfort in homes and in offices is now a significant portion of the total energy consumption in the country. So, and going forward now, as we become more affluent, we start demanding more cooling, then this becomes unsustainable. So we have to look at both active means of managing our energy and passive means. And passive means would, of course, mean that we have to look at construction and construction materials, construction technology, and construction methodology, which basically reduce the demand for heating. So there's a lot of research going on trying to improve or increase the thermal efficiency of the construction materials, and looking at the building envelope as a whole to ensure that there is minimal heat gains into the house from the building material perspective. So a good amount of research is going on in developing materials which are thermally efficient. So a little bit of background. I almost have to cover this in order to give you an appreciation for how things are shaping up. The first thing is understanding cement. Cement is basically not a new material. It's been in existence for 200 years. The production process also has not changed much in the last 200 years. The one thing that has changed, of course, is the efficiency of the cement production plants. Today in India, we have cement plants which are operating at peak efficiency, and Indian cement plants, in fact, are operating probably at the highest efficiency in the world, if not competing with countries like Germany and Japan in terms of efficiency. So we've actually squeezed every little bit in terms of production of cement. What is cement? Now, cement itself, if you look at it, basically has four major ingredients that we identify, of which the main ingredient, of course, is lime, calcium oxide. Then there is silica. These are the two main ingredients of cement, CaO and SiO2, silica as we call it. These are the two major ingredients of cement. Then we have alumina and iron. And how do we make cement? We typically take limestone, clay, and fire it in a kiln. So what you see in the figure on the left hand side is a kiln, and it's basically fired to a temperature ranging between 1400 to 1600 degrees Celsius, and that's where the energy consumption goes. And what we form are primarily calcium silicates. So cements are calcium silicates, and in order for us to unlock this, to look at alternate binders or somehow be more energy efficient, or look for alternate materials to produce cements, we have to address this calcium silicate chemistry. So a little bit of chemistry here. The cements are primarily calcium silicate. So the reactions that you see on the top, there are two primary compounds, the tricalcium silicate and dicalcium silicate, C3S, as you see on the very top, and the C2S. These two combine with water, and that is indicated by this H here. So if you see the H, that is water, and they form what is known as CSH, which is the calcium silicate hydrate. It is this calcium silicate hydrate that is responsible for the strength of concrete or the strength of hardened cement. Now, there's also a lot of lime that is produced in the reaction. The CH that you see here is the lime. So cement, as it hydrates, produces a lot of lime as a byproduct. And that is what makes the cement very alkaline. So one of the early attempts at trying to reduce the cement consumption was to look for alternate sources of silica. And we know of several sources of silica. Now, if you look at waste materials like slag, which is basically a byproduct of iron refinement process, fly ash, which we get by burning coal, and metakaolin, which is basically produced by sintering of clay. These have abundant silica in them. And because cement hydration produces lime, CH, if I have a source of silica, it's able to combine with this lime that comes out of cement hydration, and I'm able to produce additional CSH in the system. And this is a mechanism that has been put to test. We call this the pozzolanic reaction. And pozzolanic reaction has been used wherein we basically are able to produce additional calcium silicate hydrate in the system by dosing these additional sources of silica. So the additional sources of silica can now replace some cement. So I don't need as much cement because now I'm producing additional CSH from this waste materials. So that basically was the first attempt at reducing the cement content in concrete. And now it's very well established, where to the point that commercially cements that you buy now are coming with a good percentage of the cement replaced with these materials of slag and fly ash. And please bear in mind that slag and fly ash are waste materials. So it's basically killing two birds in one shot. I'm reducing cement consumption, and I'm basically also getting rid of a waste material in a beneficial manner. So just to give you, show you what these products look like. Slag is basically what we get as the waste product after refinement of iron from iron ore. And basically it is produced at a very high temperature. And when iron is in a molten state, slag is what floats on top of the molten iron. That is at a temperature of anywhere from 1800 to 2000 degrees Celsius. And that is quenched very rapidly. So they take it literally and throw it into water. And what comes out of it is like a glassy powder, and that's ground in a very fine form. And so it's available in a granulated form. And that slag is very rich or has a very high reactive glass content. And this is rich in silica. Similarly, metakaolin, what I'm showing in the bottom side here, is what you get by sintering some clay. Even that is moderately reactive, it contains silica. So these are all good substitutes for cement because they contain silica and also calcium. Now coming to the fly ash, which is also a waste material, it's basically the ash that is produced when we burn coal, and it is collected using electrostatic precipitators. So basically, when we have a thermal power plant, the flue gases as they're escaping from the boilers, these contain a lot of ash, and it is that ash which is collected using electrostatic precipitators. And that ash, as we are now looking at carefully, basically contains silica and sometimes also some calcium. So basically, it is all the right ingredients that we could use for making of cement, or basically replacing cement. And this fly ash is basically available in the form of a grayish powder. And basically the way it works is that when I look at a supplementary cementitious material, so if I look at any of these materials that contain silica and calcium, then I can use them to supplement cement, hence the term supplementary cementitious material. And the way we use them as cement replacement is to basically look at cement, main ingredients of cement on the left-hand side. It's calcium oxide and silica. And the main ingredients of the slag or the fly ash and metakaolin is the silica. So basically what I'm trying to do is to replace the silica in the cement with the silica that I'm getting from these waste materials. And basically the silica replacement relies on this pozzolanic reaction, where cement reacts first, produces lime, the calcium hydroxide, And the calcium hydroxide then consumes the silica that's available in these waste materials like slag or fly ash, and gives me more strength-giving calcium silicate hydrate, which basically allows me to produce the same volume of reaction products, and therefore I'm able to give you the same performance or the same strength with lower usage of cement. Now, coming to fly ash, this is a peculiar problem for India. So the map that you see there, shows the different countries in terms of their coal consumption and hence ash production. India, we are hooked on to coal. It's not just India. In fact, it's India, China, and US. We are the largest consumers of coal, and most of this coal is consumed in producing electricity. Because today, the cheapest form of electricity comes from coal. In India, currently our consumption is 536 million tons of coal go into generating electricity. Now, the biggest problem that we have in India is the coal that we burn is not the best grade coal, which means that when we burn the coal, we produce a lot of ash. Most of the coal that we mine in India, in Bihar or in Jharkhand, this basically is not the best grade coal, and so we end up with a lot of ash. And our ash content is much higher than the numbers that we get from around the world. So ash content typically is upwards of 32%. In fact, numbers are more like 50%, which means that for every kilogram of coal that I'm burning, I am left with half a kilogram of ash. And this ash, if I do the projection, then if you look at the bar chart on the right-hand side, our numbers are just going to explode because we've been adding more and more coal burning thermal power plants to meet our energy demand, and our projected energy demand requires enormous amount of electricity, and we are relying more and more on coal. And so by the time we go to 2030, 31, we will be producing about 600 million tons of ash, fly ash. Now, the issue with this ash is that it is not very it is not in a useful form that can be utilized by other industry. So if you look at the graph here, the ash generation are the blue lines, and the green lines are the green bars show the percentage utilization. And if you look at the numbers from 15-16, our utilization stood, in fact, at close to around 50%. It was around 45 to 50%. Projected forward now, if we are not able to come up with innovative ways of getting rid of this fly ash, we'll end up with more fly ash, and disposal of this fly ash will become a problem. So we have a problem of plenty when it comes to fly ash. This is a material that is being produced more in quantity than we can possibly get rid of. So for us, in India in particular, the problem is one of disposal of fly ash. Now, this fly ash happens to contain silica, therefore we can look at it as a cement substitute. And because we also have a growing demand for cement, so this is a win-win situation for us in India to focus on fly ash as a construction material as replacement for cement. And already a lot of work has been done on this. One of the biggest problems that we face with fly ash is the large variability in composition. It is very variable from source to source. I'll just show you in the next few slides. It varies from source to source. So if I collect fly ash from two different thermal power plants, I'll get two very different kinds of behaviors. It also varies on the raw feed of coal. What happens occasionally is that we get good coal that is imported from Australia. It's good anthracitic coal. That coal then has lower ash content, and the fly ash that is produced is much more reactive. It contains more reactive silica in it. So that then becomes more suitable for cement replacement. But a lot of times when we burn Indian coal, then we end up with fly ash, which is not as reactive, and so it's not preferred as much. So the typical problem that we deal with fly ash is its low reactivity. It doesn't react very quickly. So that means if we really need to figure a way to use this material, we have to figure a way to make it reactive. Now, what does fly ash look like under SEM? If you actually put take fly ash and study it under scanning electron microscope, it's beautiful. You get different morphologies, so it's a material scientist's delight. You get these iron-rich spheres that you see. Then you have a lot of quartz in fly ash. Quartz is nothing but sand. So, which means that the impurities that we basically that come into coal at the time of mining, and these impurities are in the form of sand, that impurity stays, and basically you are stuck with a lot of sand. And remember, silica is primarily Si and O, and basically, which means that if I was to look at fly ash and look at the silica content, a large percentage of that may be present in the form of quartz. And quartz is sand. Sand is one of the most inert materials known to man. It doesn't react. Therefore, this is something we should be cognizant of. Is we have to look at fly ash and see what is the quartz content in there. There's a lot of carbon. Some of the older thermal power plants are not very efficient, so it's not unusual to pick up unburnt carbon. We can have unburnt carbon in our fly ashes, sometimes as high as 5 to 10%. Which of course means that we could have burned that coal and extracted more energy, but this also has consequences for construction because carbon is an absorbent and it starts absorbing moisture, water, and because cement hydration is a water-based reaction, this starts upsetting the water balance in the system. The most important part of fly ash, which we are all interested in, are these nice spheres that you see at the bottom here. These are what we call cenospheres. They also contain silica, they contain some alumina, and these are glass. Basically, the composition is an aluminosilicate glass. And this is the reactive part of fly ash, and this is what we are interested in. The size of these cenospheres typically ranges from 10 microns and below. So they're basically small spheres that are present in the fly ash. A side note, incidentally, the cenospheres, because they're pure glass, are sought after as abrasives. So the cenospheres are lapped up or consumed by the abrasives industry. The problem is that if I take fly ash, probably about 10 to 20% of the total volume of fly ash or total mass of fly ash may be present in the form of these cenospheres. So typically what is done is that they sift through the material, they separate the cenospheres, and then they dump the rest back. And once you remove the reactive part, nobody else is interested in the non-reactive part of the fly ash. Just to show you the cenospheres, just to show you that these are beautiful spheres that basically exist inside the fly ash. And it is these spheres which are made of pure glass. It is that glass that we are interested in. And the glass is the reactive silica that I'm seeking as my cement replacement. Just to show you the variability of the material, we collected fly ashes from different parts of the country. Mostly, of course, they were in the peninsular part of India. And we did an oxide analysis. So what I'm showing you here is a table of the oxide analysis. Typically, you could do an X-ray fluorescence spectroscopy analysis, and you could determine what are the oxides that are present in the fly ash. And basically, this table shows you the oxides that are present in the fly ash. The alphabets on the top, B, D, K, M, these are all designations of the different thermal power plants. Now, if you look at these numbers, right, the numbers don't look very variable. If you look at the two prime ingredients in fly ash, the silica and the alumina, SiO2 and Al2O3, on the surface, it looks like the difference is very small. Yet, when we started using this fly ash in cement as cement replacement, we saw a very large difference in the performance. Some fly ash was performing very well. It was giving us it was basically serving as a good substitute cement, and some fly ash were absolutely terrible, where basically we were getting properties which are worse than what we were getting from pure cement systems. So there was clearly something that was hidden that was not being indicated by this oxide analysis. The other interesting thing is that our fly ash typically has very low lime content in it. This has consequence. I'll talk about this in the next few slides. Is that our fly ashes typically are what we call low calcium siliceous fly ash. That's our the fly ash that is predominantly produced in India. Now, when we talk about glass chemistry, so we started looking into the chemistry of glasses, And we found that the aluminosilicate glass that is present in the fly ash, people have already done a lot of work on that. And basically, one could do X-ray diffraction to study the nature of the glass. If I show you the X-ray diffraction signature of glasses, different types of glasses, there are two types of glasses that I can form. One is a low calcium glass, the other is a high calcium glass. So if I have a low calcium glass, that's of the type D or B. So if you see the signature here, this is the intensity signature that I get from XRD. It has a hump sort of a thing. There is a hump here that you see, and the hump is centered close to 30 degrees in the XRD spectrum. Whereas if I look at high calcium glass, so this is glass which contains more calcium in its structure, that also forms a hump. And this hump is produced whenever you have amorphous material in the, or amorphous phases present in the material. And glass is amorphous. So basically this hump that you see here for high calcium glasses is basically centered closer to around 20 degrees here. So what we found is that there is different types of glasses, and the fly ash that we produce in India is a low calcium fly ash, and the difference that comes about is that the high calcium glasses are typically more reactive. And what that means is that if I was to put it into a cement system, it would be very reactive, and basically I would get a good substitute for cement. Whereas if I go with low calcium glasses, then they are not reactive. I have to basically kickstart the process somehow and get it to become reactive. Now, the other problem that we found is, if I go back here, is that a lot of our silica and the calcium that is, the silica and the alumina that is present in the fly ash is present in inert non-reactive form. So basically I have a lot of quartz in the system. I have a lot of mullite. With the quartz and mullite, these are two inert materials, and they are basically also, or they also contain silica and alumina. So basically, because I have high crystalline content present in the fly ashes that are produced in India, most of the silica and alumina that is indicated by the oxide analysis is present in this inert form. And what that means is very little of the silica and alumina is available to us in a reactive form, which basically means that the fly ashes we are dealing with also have a low, not only are they not reactive, but they also contain low reactive content. So I just want to show you the numbers in terms of reactive silica and reactive alumina. So now if I look at fly ashes, if you remember those 10 fly ashes that I had presented before, the graph on the left shows the blue lines show the total silica content that is present in the fly ash. So the blue lines are basically what we had from the oxide analysis, and that looks fairly consistent. But then we started determining what is the silica that is present in a reactive form. If I do that, then that is shown in the green lines here. So if you look at it, suppose I take one fly ash B, 55.45% of that fly ash is total silica, that is the SiO2 that is present. But only 23% of that is basically available in a reactive form. So which means rest of the silica is present in the form of quartz, and this quartz is sand. It is non-reactive. So what is happening is that while I am getting fly ash, a very low percentage of that is available in a reactive form. So this is one of the biggest challenges that we face. And now if you look across all the fly ashes, you find that the numbers start showing up very starkly. So you see that now the differences between the fly ashes are starting to show up. So if you look at the green lines, I have one fly ash which contains almost 23% reactive fly ash, reactive silica, and the other fly ash which contains only 13%. So on the surface, while the total silica content was uniform, the reactive silica content is basically very different, and that's what leads to these differences in the reactivity. So from here now, we started branding our fly ashes. So we basically, the work that we did in our lab was to recognize that the reactive silica present in the fly ash is low. So from there, we developed a metric. So we can now develop a number which allows us to see what is the optimal replacement of this fly ash in cement, so that we don't compromise the performance of concrete. So we can now tell you precisely what is the extent to which you can replace cement with a certain fly ash based on its reactive silica. And using this, we are now able to replace fly ashes to the tune of 50% of a cement. So we can now start looking at fly ashes which contain 23% reactive silica, and there we can replace up to 50% of cement with fly ash and produce equivalent concrete, which gives you the same strength and the same performance. Whereas when you talk about fly ashes which contain low silica content, like 13.45, as I've shown in this box here, this fly ash you can only replace at a smaller content percentage, and with 13.45 you can likely replace 20% of cement with this fly ash and still achieve the same performance. So now we are basically talking about an efficient replacement of cement with fly ash so that the total performance itself is not compromised. Similarly, now on the graph on the right shows you the alumina content. So it's the Al2O3 content that is present in the fly ash. And again, you see the big difference. While the total alumina content shown by the blue lines is more or less consistent, the reactive alumina content that is present in the fly ash is much smaller, and it is inconsistent across the different fly ashes. Now, when we're talking about cement chemistry, it's only the silica that we focus. But this reactive alumina becomes important when we talk about alternate binders, and I'll talk about that in the next few slides. So basically, just a recap, fly ashes that we have in India basically contain are low calcium siliceous fly ashes. They contain low reactive content. And basically classification of these fly ashes is essential. We can basically then determine the exact level of replacement of cement and optimize the usage of this fly ash. So working with the cement companies now, we are starting to optimize the clinker. Clinker is basically the raw, what is ground to make cement. So OPC is ordinary Portland cement. It's made using by grinding clinker, and we add a little bit of gypsum in this. This is commercial cement that's available. So we are basically trying to take away the slice of clinker, replace it with fly ash, or sometimes using slag. Now slag is much more reactive, therefore we can flip the equation there. So when it comes to slag, we can actually have more slag than clinker and basically produce cements which have basically very low amount of clinker, which basically give you the same strength and performance as regular OPC. Now, next, what I want to talk about is move away from the calcium silicate chemistry, which is what went into making ordinary Portland cement, what we use today commercially, what is commercially available. What I want to talk about is alternate binders. So we are looking at alternate binders which do not use cement at all. And these are what we call aluminosilicate binders. So the chemistry is different. These are not calcium silicate binders. These are aluminosilicate binders. And we are also talking about magnesium-based binders. These are binders which are derived with magnesium as the source or the spine, the backbone. And these are being actively researched as alternates to calcium-based cements. And basically the source, again, is all these raw waste materials that I talked about, fly ash, slag, ash that is produced when you burn the rice husk, known as rice husk ash, and the metakaolin, which we get from calcining clay. Here, the difference compared to cement chemistry is that we do not require a calcium source. The chemistry is different. Now, how does it work? We take fly ash, which, as I said, contains reactive alumina and silica. We basically add an alkaline activator, and we basically have to subject it to a little bit of temperature. So the temperatures can go up to 40 to 60 degrees for a small amount of time. What we end up with is a binder, which is a sodium aluminosilicate hydrate. It is different from calcium because now here the base chemistry is a sodium based chemistry of aluminosilicates. And this material is stronger than what I get from cements. And it is derived only from fly ash. There's no cement that is used. Similarly, we are talking about alkali activated slag. So we take slag, mix it with an alkaline activator, which is basically just sodium hydroxide. And sometimes we may add water glass or sodium silicate into it. And what we produce is a binder which is very strong. And because slag contains a lot of calcium in it, what we end up producing is a calcium aluminosilicate hydrate. So here, in both of these materials now, aluminum becomes the centerpiece more than silica, and it's more aluminosilicate chemistry that is what needs to be understood to make these binders. So basically, when I take fly ash or any source of silica and aluminum and I put it in an alkaline environment, it basically releases the silica and the alumina. And with time, what happens is the silica and the alumina cross-link with each other with oxygen atoms at the corners. And what we get are these long inorganic polymers, which we call them or they are also called as geopolymers. So now, these geopolymers are alternate binders that basically a lot of research is going into as possible cement substitutes. Now, again, the same challenges as what we have is we have variable feedstock when it comes to fly ash. The other issue is basically you have to use stronger chemicals. So we need high alkalinity, which means that I have to mix it with sodium hydroxide solutions. And people have done work using 8 molar or 10 molar sodium hydroxide, which is extremely caustic. So these are the two drawbacks that currently people are looking at. And occasionally we may need temperature curing. So we may have to elevate the temperature just to produce a stable binder. Now, what we have done in our lab is to basically understand the chemistry of the system. And through an understanding of the chemistry of the system, now we are able to optimize the usage of these of the activating solution to the point that if I take fly ash, we determine the reactive alumina content. So that's shown here. We are able to add sodium silicate, which is water glass, and sodium hydroxide with this. We are able to adjust it to the precise amount that is needed so that there's no wastage. Then we add water to this, and we are able to bring the processing condition down such that we are able to process it with the molarity of sodium hydroxide of 3. So we're able to produce geopolymers in our lab now at using 3 molar sodium hydroxide, which is a lot less caustic than 8 or 10 molar sodium hydroxide. We're also able to bring the curing temperatures down to 40 degrees Celsius. Now, previously geopolymers were produced at 85 degrees. Now we are able to produce the same material at a lower processing temperature of 40 degrees Celsius. So which means that basically 40 degrees temperature is basically summertime temperature in India. So we should be able to now produce this material without the requirement for additional curing or energy for curing. Now, we've actually working on a patent of this process where we take the fly ash, we determine the reactive silica and the alumina content in this. We optimize the activator and blend the fly ash with the activator, and we're able to now produce this material, which is basically on par with cement. And we were basically thinking of calling this product geocement, which basically essentially contains fly ash. Fly ash is the predominant material in there. Of course, it's been blended with some sodium hydroxide and sodium silicate in a powder form, and it's available in a powder form. So you simply take it, mix it with water, and you leave it at 40 degrees Celsius, cure it or leave it outside. It cures and gives you a product which is similar to cement, and basically one is able to make concrete with this geopolymer material. Going forward now, even to reduce the requirement of that 40 degrees temperature, we are working on blends. So we're working on blending fly ash with a little bit of slag. So take fly ash and slag, which are basically, again, two essentially post-industrial waste materials. We're looking at blend which contains 80% fly ash and 20% slag, blending it with the required amount of sodium hydroxide and few other activators. And now we are able to produce binders which give us strengths of about 80 megapascal, which is more than what cement paste gives at room temperature. So this is also something that we're working on, where we're able to produce binders which can be used for making concrete under ambient conditions. Absolutely no temperature is required for, or higher temperatures are not required for curing this material to achieve the strength that we need. Now, coming to other developments in this area, some of the researchers around the world are now getting excited about these magnesium-based cements. Now, basically, the process is very similar to what nature gives us, and that is biomineralization. The whole point is to basically mimic the process that goes into making these corals, shells, etc. And basically, if you look at the chemistry of these shells, they're made of this marine cement, and if the composition wise, they contain calcium and magnesium, and they're basically carbonates of calcium and magnesium. The process, the biomineralization, which takes place over decades or centuries, now that process has to be condensed, and people are actively working on basically shrinking that process so that we can achieve this biomineralization in a matter of hours or days instead of decades. And that is the basis for these magnesium-based cements. There are already some companies that have been set up, several patents that have been taken to look at magnesium silicate-based cements as well. Now, this is again where we're mimicking nature again, trying to produce magnesium silicates. Now, magnesium is available in abundance in oceans. So basically, the source is to use the ocean to be making these cements. The production temperatures, as they've been looked at, basically run at about 650 degrees Celsius. But people are talking about these magnesium silicate based cements basically also being able to sequester carbon dioxide. So not only is it you processed the processing temperature lower, it is processed at 650 degrees Celsius, but also it has a positive carbon footprint in the sense that it can actually sequester more carbon dioxide than what goes into making of this cement. So magnesium silicate based chemistry is being explored very actively. And production of this cements is being looked at in order to replace the calcium-based cements for the future. Now, the problem with a lot of these alternate cements and alternate binders is the issue of long-term performance. And that is, while we tested in the lab, these are all short-term. Now, the whole point is how durable are these in the long term? And that is one of those things that is being studied now actively, where the durability aspects of these binders are being explored. And basically, once the durability aspects are evaluated and they're investigated, then whatever weaknesses are there in the durability, long-term performance, those can be addressed and basically suitable design procedures can be developed with those. But these alternate cements are slowly coming into mainstream, where we're seeing more and more structures being made using these alternate cements, which are either derived completely from post-industrial waste, or they use a chemical process which is basically mimicking nature. So basically, in that sense, we are sustainable. Right. Now, coming to these geopolymers that we have, already while the structural applications, which would put them into use in buildings or structures which are able to, which carry load, while those are still being developed, I think alternate uses have already started. And one of the biggest uses for this geopolymers is happens to be in this acid-resistant precast pipes. Most of the pipes, precast pipes that are used for sewage disposal, basically carry sewage which is very acidic in nature, and it eats into the cement pipes. Typical cement pipes get damaged very quickly because cement based or cements which are derived from calcium based products are very prone to acid attack. Whereas these geopolymers that are produced from fly ash, basically, which are the sodium aluminosilicates, are very acid resistant. Now, what we've done is working with some of the, or realizing the inherent advantage of this material, we started working with the cement pipe manufacturers. They use an autoclaving process. So basically, in autoclaving, in order to for the cement to gain strength rapidly, the pipes are steam cured at a temperature of about 85 degrees for about 6 to 8 hours. So because the elevated temperature was anyway being used for a cement-based product, we worked with the manufacturers to develop this geopolymer product. So basically now you take fly ash, mix it with this sodium hydroxide and alkaline solution, and you steam cure it. And basically I have the high temperature that is being provided to the material. It gives me a very strong geopolymer, and geopolymers are very acid resistant. So basically these precast pipes, which are now made of geopolymer instead of cement, are already coming into production, and the inherent advantage of acid resistance of geopolymers is being put to use here, and used making a material which is completely a waste material in the form of sodium hydroxide, in the form of, sorry, fly ash. The other material we are looking at is in the for tunnel liners. Whenever you have a tunnel, when you have a TBM that goes through, the lining is supported using these precast liners, and these are made of concrete. Those precast liners are now being replaced with this geopolymer material, which is made with fly ash. There's another aspect which is being focused a lot, and that has to do with energy gains. And this is one of the topics that I had mentioned about energy gains, and energy being one of those issues that we have to address if we have to look at sustainable habitat. Now, if you look at a typical house, we gain a lot of heat, and in India in particular, heat is a major issue. Now, a lot of the heat comes in through the building envelope. May I request whoever it is to mute themselves? I think we're picking up an echo. Yeah. Now, a lot of the heat comes in through the building envelope. This is the skin of the building. And the walls, which are in contact with the external environment, basically carry a lot of heat into the house. Now, the point would be if we could make these walls of a low thermal conductive material, we would basically cut down on the heat gain in the house. And if we can cut down on the heat gain in the house, we can basically reduce our energy demand required for cooling. And that is the whole concept of passive energy control. And one of the products that has become very popular in India now is this AAC block. It is autoclaved aerated cement block, and you see that here. This is basically a cement, cementitious material with a lot of air or bubbles that have been introduced into it. And once the cement sets, what you get is this porous structure, which is very light. It has a lot of air in it. And because it has a lot of air in it, it has a very low thermal conductivity. And that is being used extensively now in making these infill walls. So when you have a concrete frame, what goes between or inside the concrete frame is now being made with this AAC blockwork. Except now the AAC blocks are made of cement. So what we are looking at, the way the AAC blocks are made is by an autoclaving process. So one basically introduces bubbles into the cement paste, and the blocks are autoclaved just to be able to gain strength rapidly. An autoclaving process is used. So what we are doing is basically making the same material except using geopolymer. So we start with fly ash, mix it with this alkaline solution. We introduce bubbles into it using metastable foams. And metastable foams are nothing but basically the same material that we use in shaving foams. These are basically a shaving foam contains bubbles in a very metastable form. So basically we use the same kind of material and induce a lot of air bubbles into this geopolymer material. We're able to adapt the same technology that is used for AAC blockwork, except produce the same material using geopolymers. And now we are starting to produce not just bricks, but also these panels, which are made of AAC blockwork. Now, these panels can be used as wall elements instead of bricks, and they have very low thermal conductivity, and they're made with fly ash. So that means the embodied energy, the total energy that goes into production of this material is also much lower. What are the advantage that I gain? So I'm showing you the difference between the time of construction. So this is also tying into the efficiency of construction. So when you have AAC blockwork, and that's shown on your left-hand side, you need a mason, and basically in about 2 hours, a mason will be able to finish about 4.8 square meters of this wall. It's a very labor-intensive process because the joints have to be properly made, and then the bricks have to be aligned and laid out carefully. Whereas if we make these panels, which are basically full height panels, they can be erected very rapidly. They're made of the same material, and I need much less labor. I can basically in the same time, 2 hours, I'm able to basically make about 14.4 square meters of this space. And these are infill panels anyway, so they're non-structural, they're not carrying load, but they form a part of the building envelope. So I have material with low thermal conductivity. So it's basically very beneficial in the thermal environment. At the same time, I'm basically giving these panels, which are much faster to erect, speeding up the construction, leading to efficient construction. Right. So that's basically as far as the material aspects and sustainability when it comes to the use of materials and material forms. Now, what I want to talk about is the reinforcement. This is the other thing that I had basically bulleted as what we're looking at. And just to show you what most of us structural engineers dream of, and this concept of ductility, and that is basically what you see here is everything that's gone wrong. But if you notice that beam over there and the slab, it is deflecting, but it has not failed. And today in structural engineering, we teach our students this concept of ductility, and that is a structure should be standing even if you knock off some of the supports, and basically it should be able to deflect without failing. And that is the concept of ductility. And the way we achieve ductility in most of our concrete structures is through the use of steel reinforcement, by placing it properly, by placing the right amount of steel in these concrete structures. So, but this is what we end up with. So oftentimes the requirement of ductility takes us to these extremes, and what I'm showing you here is a beam column joint. You can see two beams coming in two directions here, and then you have a column. They're basically meeting at a joint, and if you look at the amount of steel that's placed in there, the reinforcement, there's hardly any place to put concrete inside this steel cage that I've created. So in order to make my structure ductile now, I have to put so much steel that sometimes it becomes impractical. And we now have to seriously start addressing this issue of making our structures ductile and without the use of so much steel reinforcement. So what we're working on is looking away from steel, which is typically used in the form of these bars. So these are basically continuous bars, to using discrete reinforcement, where basically we use fibers. These fibers are basically smaller reinforcement. Basically, they're much smaller in length, smaller in diameter, and they form discrete reinforcement. And the whole point is that when I have a steel reinforcement bar, when concrete cracks and the crack crosses the reinforcement bar, it is arrested by the steel bar. And that is the whole concept of using reinforcement in steel. Now, if I take the same steel bar and chop it up into smaller strands and distribute them across concrete, I get this discrete reinforcement. The advantage I gain is that these little fibers act as local crack arrest. So basically, they'll be arresting the crack locally. And rather than having one big crack, I may end up with having 50 small cracks. And some of those cracks may be so small that I may not even be able to see them. And in the process, then, I can actually use my steel reinforcement much more efficiently. So basically, this is the concept of fiber reinforcement, just to show you that when I don't have fibers in concrete, concrete is a very brittle material. When I pull on it, basically, I end up forming a major crack in the material. But when I put fibers in there, what happens is every fiber is acting as a local crack arrest, and I get multiple cracks, and these cracks become very, very fine, and one is not able to see these cracks in the long run. So what I gain with adding these fibers to concrete is what is known as toughness. I make the material tougher, where it's able to absorb more energy before it fails. So how do we measure toughness? Typically, we measure toughness as the energy that is required to separate the material and create two pieces from it. So what is the energy that's required to essentially create total separation? So if I look at the stress as I'm pulling the material with fibers across the crack, now if you look at plain concrete, as the concrete cracks at FT, if I start pulling the crack apart, the stress that is resisted by the material rapidly drops down to zero, and I get two pieces. Whereas when I start adding fibers, what happens is initially there may be some drop, but then the fibers kick in, fibers start arresting the crack growth, and I get basically a stress recovery, and I'm able to sustain the stress at some level. If I add more fibers, I can go to the point where the recovery goes beyond the initial tensile strength, in which case, because I've crossed the tensile strength of the material, I may get multiple cracking in the material. So here then, instead of having one big crack, I start getting into 50 small cracks. Now, in concrete, there are different types of fibers that have already come into existence. They're being used. They go from steel to synthetic. Different types of synthetic fibers are available. Glass fibers are used, asbestos, carbon, and even some natural fibers are being used. The use depends upon the cost to benefit ratio, what benefit I derive, because fibers do cost something. The ease of applications, the certain fibers that are best suited for certain applications, and the desired level of improvement that I'm looking at. Now, when it comes to use of fibers, we are already, fibers are being used for commercial applications. One of the biggest applications is in shotcreting. Now, when we tunnel through rock, oftentimes to stabilize the rock, one puts a tunnel liner. And the way it was traditionally done was using a steel wire mesh. And the wire mesh was basically put in place, and then that was shotcrete. So shotcrete is basically like ganiting, where you basically spray concrete, and the concrete basically penetrates through the reinforcement. And once the concrete hardens, what you get is a shell of concrete, which is reinforced with the steel, and that stabilizes the tunnel liner, prevents these boulders or loose rocks from falling. Now, shotcreting is now extensively being done using fibers, steel fibers. And so rather than assemble a steel reinforcement like what you see here, we can directly mix fibers into concrete and simply shotcrete it. So this is a much faster operation. It's already being implemented in India. So two of the longest tunnels in India, the Lahul Spiti Valley Tunnel in Himachal Pradesh and the Jammu tunnels, these are all-weather tunnels which basically have been inaugurated recently. The tunnels have been stabilized by shotcreting using steel fibers. Then the other places that we're looking at the use of fibers to produce durable structures is in jointless slabs. So this is one of the places, because fibers, when they're present in concrete, even if a crack were to form, the fibers immediately, if the fibers will bridge the crack, will not allow the crack to open, and basically they will distribute the cracking. I'm able to use them in design of these super heavy container terminals, flooring of that. So if you look at this terminal or the cargo terminal yard, which is built by Amazon, where it is not unusual to see 5 or 6 of these containers stacked, and the load under that on the pavement or on the concrete structure is very, very high. So to prevent cracking in the concrete, steel fibers were used, and they've done a jointless concrete pavement. Basically, this is concrete which is done without any joints. It is one big piece of concrete with steel fibers in it, and it is very much in operation. This is a container terminal yard which was done in Chennai. Similar warehouse and storage space of Amazon in Hyderabad has also been done with steel fibers. Tunnel liners is another application where fibers are being used in precast tunnels, so that rather than use longitudinal reinforcement bars, directly use fibers in there, where I can use the exact amount of requirement of fibers and produce these liners. The other place where fibers are being used a lot is to prevent the restrained plastic and shrinkage cracking in concrete. Concrete has a peculiar property that when it dries, it loses moisture. And if it loses moisture, it shrinks. Now, when we have a long piece of concrete, and if that concrete is in the form of a slab, if it wants to shrink, its shrinkage is prevented by the subgrade because of friction. And once you prevent its free shrinkage, tensile stresses develop. And because concrete is weak in tension, it starts cracking. So it's not unusual to see cracks develop in concrete pavements. And once a crack forms, water can get in and we have all kinds of problems. So to prevent shrinkage, now polypropylene fibers are being used, and micropolypropylene fibers are very effective in reducing this cracking that is produced. So of course, when I use these fibers, it's not that I cut down on the cracking. I still have cracking, except instead of having one big crack, I have several small cracks, and each of these cracks are so fine that water cannot get into those cracks. Right. Glass fiber reinforced concrete has been used basically in this building that you're probably familiar with. This is the Chhatrapati Shivaji terminal building. The facade, the white concrete that is used in the with the architectural shape that you see has been done using glass fiber reinforcement, and the glass fiber reinforcement basically went into was used in the concrete to prevent these cracks that appear on the surface as concrete dries. Now, those cracks would have basically ruined the look of the building, and just to give you that crack-free appearance, as if it's made of a single rock, or to make it give the appearance of something that's made of rock, glass fibers were used in this concrete. Another application where glass fiber reinforced concrete has been used extensively is in architectural forms. I just want to give you an example of one of the projects which I was involved in, and that is, if you look at this is a structure which has this Gothic forms, which are basically made of the natural stone which is found in that area, except that stone started crumbling with age, and that was replaced with this castings which are made of cement, which is reinforced with glass fibers. The glass fiber was there to prevent cracking in concrete, or to basically reduce the appearance of cracking in concrete. And all these white stone were replaced with white cement, which was reinforced with glass fibers. Another application of fibers is in the use of ballastless track for high-speed train. Now, a high-speed train is becoming reality in India, and now the new method of construction for this train system is to go with ballastless track. We don't have the ballast, or the stone that you see typically, which acts as a cushion material. In this ballastless track, the track is directly rested on concrete. Now there, typically very heavy reinforcement goes into the ballastless track, because we cannot afford for the ballastless track to crack. It will create all kinds of unevenness in the movement. Now, the typical steel reinforcement of this calls for very heavy steel reinforcement. But if you look at it carefully, steel is provided. Steel that is provided is not uniformly utilized. Whereas when I add fibers into it, I can achieve the same objective by dispersing the fibers more efficiently and providing them where they're needed. Working with the high-speed train system, we were able to actually develop a concrete mix design which used fibers. And with the use of fibers, we're able to cut down on the use of steel in this ballastless track. I just want to show you the numbers here. That by using 5 kilograms per cubic meter of steel fibers in there, we were able to bring the steel requirement down to basically from 1347 millimeters square per meter of the ballastless track to 785 square millimeters of steel per meter of ballastless track. In terms of crack width, if I calculate, or we have to expect cracking even with steel reinforcement, and the cracking with steel reinforcement, crack widths that we were getting was about 0.48 millimeters. But with the use of steel fibers and reduced steel quantity, steel reinforcement, we're able to bring the crack opening down to 0.2 mm. So basically, we gain overall, we use lower amount of steel, produce a structure which basically has smaller crack width in it. It's also, steel fibers are also coming mainstream, and that is when I add steel fibers into concrete, I can actually start looking at improvements in structural performance. We've used steel fibers to enhance the shear capacity of concrete. So just to show you that when I have a beam that is tested in shear, basically when I have no steel fibers in it, it fails in a brittle manner. With 0.5% steel fiber, I gain in the peak load and also ductility. If I add about 0.75% volume of fibers into concrete, I basically get a very ductile response from the beam. So basically, I can now start bringing these fibers mainstream instead of regular steel reinforcement in the fibers. So that's as far as regular steel fibers go. But what I want to do now is to introduce another material, which is now also catching on in terms of its use, is where we basically start pushing the material to an extreme. And this material is what we call ultra high performance concrete. Now, the whole concept here is to look at material ground up. Here, typically what we do with concrete is to take the material and then add something and see what is the improvement that we get in the performance of the material. in ultra high performance material, the object is to start improving the material behavior from a nanoscale, then the micro, the meso, and then ultimately you would get an improvement in the macros behavior. So if you look at the engineering the material by using nano additives, at the micro level, one goes for better packing of the material. We pack it better. At the meso scale, we bring in fibers. And then, of course, at the macro scale, what we get is an overall improvement in the response of the material. So through processing then, if I look at a cement matrix, I'd be lucky to get about 3 megapascal in tensile strength. If I directly add fibers into it, I may gain a little I may gain a little in terms of its peak stress and ductility. But if I follow this approach, then I can start getting material which basically starts behaving like steel. I start getting much higher tensile strength. I also start getting much improved ductility. So this is now cements or cement-based materials which are engineered for performance, where I'm starting to get material behavior which starts mimicking what I would traditionally get from steel. But of course, this is only possible through processing the material. I have to understand how to pack the material better, and also it demands a lot of fiber. Now, just to show you, yeah. So what kind of packing are we talking about? Here's the just a CAT scan of an ultra high performance concrete, and you see the kind of fibers that get packed into it. So this can only be achieved through processing. A lot of processing goes into this ultra high performance material, where we pack in fibers into the material and create a dense pack of fibers into the material. What can I achieve with this? This kind of a performance. So this is an ultra high performance concrete, which basically starts behaving like steel now. Just to show you a beam made of ultra high performance concrete, and one starts getting a deflection behavior, which basically makes it look like steel. Where are we going with this? These products are now commercially available. Ultra high performance concrete is now being commercially produced. So just to show you a comparison, the steel beam is shown in red here. Typically, to achieve the same performance from, or the same strength and performance from regular concrete beam, the size of the concrete beam is shown here. This is the concrete beam, which is basically would give you the same strength and stiffness as the steel beam shown in red here. If I pre-stress that, I would probably, maybe I can reduce the size a little bit. But if I start now using this ultra high performance concrete, this is the size of the beam, which is shown on the extreme left, labeled ductile, which basically gives the same performance as steel. So now I'm talking about a very efficient use of material, which basically is high performance. So I'm using less material. So using less material has tremendous advantages. That is, I of course use less material, which is in terms of volume consumption. But for civil engineering structures in particular, less material means less weight, and which means I'm basically cutting down on the primary contributor to the requirement in design, which is the weight of the structure itself. So if I cut down on the weight of the structure, I need lighter members, smaller members. Just to show you the load tests that were performed on this, on a beam that was 13.4 meters made of this ultra high performance concrete, and one starts getting behavior that starts looking more and more like steel. And ultra high performance concrete structures are becoming reality now. This is a structure in Korea, where basically this structure looks as if it was made of steel, but in fact it is made of ultra high performance concrete. The dead weight, which in the case of bridges amounts to about 65 to 70% of the structure, is tremendously reduced with this material. So as a result of that, I can now start making structures which are more slender, and I can achieve slenderness ratios of 1:30, which is not conventionally possible with concrete. So this is basically one of the directions in which now we're starting to move in terms of efficient use of materials which are more sustainable in the long term. So now, what are the challenges with some of these things that I've talked about? Challenges, of course, are that we currently don't have all the test protocols that we need to characterize the material properly. and we don't have all the design codes. Well, some structures have been put in use. There is no proper design code or guidance which is available when you want to use alternate reinforcement in the form of fibers, or when you want to use ultra high performance concrete. The other biggest problem that we have is that our design codes are strength based. Everything is measured in strength. What is the strength that is achieved? What we ignore in most of our conventional design codes is the tensile contribution of concrete. Because concrete is very weak in tension, all our design codes that have been developed over the past several decades completely ignore the tensile contribution of concrete. Now, whereas when we add fibers to concrete, or when we are talking about ultra high performance concrete, it is the tensile property of concrete that I've improved. Now I've made concrete behave like steel in its tension capacity. So I need to completely change my way of thinking if I want to start using these alternate materials in construction. So the bigger problem, of course, with these materials, these newer materials, is production. There are very few production facilities that are available that will give you these materials of a consistent quality that can be used so that you get a reliable result. Right. Now, coming to alternate construction methods and rapid construction methods, there are, of course, several construction methods that are coming in vogue now. In concrete, we're talking precast systems, which are very fast to erect, because basically the elements are cast in a factory, they're brought onto the site, and they're assembled. Another form of construction, which is something we're looking at, is basically this 3D reinforced system for walls and slabs. And what it consists of is a mesh of steel. So you see the mesh of steel here, and it has an EPS core, expanded polystyrene core. So now this comes as a unit. So the steel mesh with the EPS core is one unit. And basically what is done is two concrete covers are put on top. Basically, we cast concrete in two layers, the outer skin and the inner skin. And we can construct the entire structure using this system. Just to show you, so this is the steel mesh with the EPS core. The entire system can be assembled. The whole system gets tied together. You can basically tie the whole house together. So you see the tying of the system here. And one can simply come and shotcrete or gunite concrete on both sides, and you have a house that is ready to use. The biggest advantage I get from this method of assembly or construction is it's very rapid, because I'm bringing these preformed systems which are tied together. The other advantage again is lightweight, because I have only two skins of concrete which are about 50 mm thick each. It's very lightweight. It has an EPS core. That means in the middle between those two concrete skins, I have expanded polystyrene, which is A, lightweight, and B, is a bad conductor of sound and heat. So basically, I gain in thermal efficiency. So this is rapid construction technology that we're working on, which basically also gives me the advantage of thermal and acoustic comfort. So in addition to savings in the material. So this is one of those rapid construction technology, which I think going forward for a country like India would become quite popular. Right. So coming to near the last part of my presentation, where I wanted to talk about the other end of the spectrum, where we're talking about pushing the envelope. So what is shown here is the skyline as it has evolved. So if you look at 1930s, the tallest building was the Empire State Building. And as we start moving across the decades, as we're coming to the left, we've come to Burj Khalifa, which is currently, of course, the tallest building at about 850 meters. So this has been possible because of advances in technology, advances in construction methodology, construction technology. But more importantly, I want to point out something that has perhaps gone unnoticed. So if you start looking at the structures to the left of Type A 101, these structures are concrete structures. So if you look at 1930s, 1940s, 50s, even 70s, the tall buildings of the world typically had steel structural systems. So the main structure was made of steel. But then as concrete technology developed, as we started developing methods of pumping concrete, of producing concrete, which is of very high strength, very high ductility, now concrete has become the favored material for high-rise construction. So the technology changes that have taken place include pumping, which is one of the most advanced, most important or significant advances that have taken place. So if you look at Burj Khalifa, concrete was pumped 850 meters, of course in different lifts, but concrete was delivered at this height. So that has made possible now the possibility of going higher and higher because we can pump concrete from the ground. Of course, that means surmounting several challenges to make this pumping technology possible. The other advantages of concrete is fire. It has much higher fire resistance than steel, so it is becoming the most popular material of choice material for high-rise construction in particular. Now, just to give you an idea of the concrete as a segment in buildings, if you look at the super tall buildings, now, if you look at the 100 tallest buildings in the world, 59 of these are in Asia. That should tell you the dominance of Asia in the latest construction. 23 are in the Middle East, and which only leaves about 18 in the rest of the world, which includes Europe and US. So in terms of tall buildings, most of the innovations are taking place in Asia, South Asia and Asia. And concrete is the dominant material. 93% of the super talls that are being built in Middle East, these are built with concrete structural systems. Now, if you take the tallest buildings, one is the Jeddah Tower, which is, of course, scheduled to be completed in 2021, which will be 1 kilometer in height, built in Saudi Arabia, will have a complete concrete structural system. And of course, Burj Khalifa has a concrete structural system. So just to show that concrete has come of age now, it's being used in more and more in the building systems. Just to show you that concrete share in structural buildings, super tall buildings. So 1930s, the light blue is steel. 98% of the buildings, the tall buildings were steel. Now, if you come across the decades and come to 2018, by the time you come to 2018, the share of steel has shrunk to a small number. It's only 9%. The concrete is gaining in numbers. It's come to about 40-50%. And if you look at this concrete combined with steel in the form of composite construction, then basically about 60 to 70% of the buildings that are built either have concrete, pure concrete, or concrete composite construction. And all this has been possible because of advances in developing or producing concrete, which is high strength, pumpable, of course, is much more affordable than steel, and all the construction techniques that have come into being. Okay. Yeah. Now, one of the quietest revolutions that has happened is in construction of concrete has been with transportation and placing of concrete. So one of the challenges, like I mentioned, is with pumping. Now we are able to pump concrete. Concrete is being pumped about 500 meters in one single lift, which is not a mean achievement. But we are also talking about other advances like self-leveling, self-consolidating concrete. And of course, the holy grail is formless placement. So that's where we are all headed towards in concrete construction. So when we're talking about all of these, we have to start looking at something that a lot of us in concrete technology and in structural engineering have ignored, and that is what we call the rheology of concrete, the flow behavior of the material, and how we can engineer the flow behavior of the material. A lot of work has gone into the strength of the material. That's what we are focused on. Now we're starting to understand, or as engineers, we're coming around to the fact that we have to be able to look at processing the material so that it flows the way we want. It behaves the way we want when it is placed. And just to show you where the whole story started with placement is the need for self-consolidating concrete. So self-compacting or self-consolidating concrete came into being and are now being used quite successfully. But the whole need for it started when people started realizing that when you have a heavy congestion of steel, like what you have, let's say in a typical precast post-tension girder, with a lot of steel sometimes is very difficult to place concrete. And you don't realize that the concrete has not penetrated into the formwork. It has not penetrated through the steel until after the formwork is removed. And what is shown here? So you can see that the concrete has not gone through the steel, and what you're left with is concrete that is not properly bonded with the steel. You have a lot of these unconsolidated pockets, which compromises the strength. Similarly, this is another example where which can become scary, is when I have a mesh of steel or a cage of steel in the form of a pile. Now these are cast in situ piles, where the mesh of steel is lowered into the ground and concrete is poured. Now this is an actual photo of a pile that was exhumed. Basically, it is pulled from the ground, and this is the shape of concrete. Now the entire building is standing on this pile. Now, of course, that has the potential of undermining the capacity or the safety of the entire building. Now, the way the people started realizing that we are not paying enough attention for in terms of flow behavior of concrete. Concrete has to be able to flow, and you can see from this photograph here, it did try to flow, but then it was not able to flow through. You can see these pockets of concrete sticking through the steel. So what we have to now start thinking about is concrete that basically starts flowing like water. It basically, here what you have is behavior of flow of a very viscous liquid. So it got stuck at a certain point, and the steel reinforcement acts like a sieve. It basically starts acting like a cage, and it traps this viscous liquid and doesn't allow it to penetrate. So then came self-consolidating concrete, where people started producing concrete that flows like water. And the same precast beams made with SEC now have this beautiful finish where concrete is able to penetrate even through narrow gaps, small gaps between the reinforcement. And basically now we're able to use this material in different architectural forms. We're able to create these beautiful forms with concrete because now we have a concrete that's able to flow. It basically fills all the corners properly, and we get these nice crisp shapes that are available, which are aesthetically pleasing. So I hope this video works. I just wanted to show you an example of self-consolidating concrete. We have done this on our campus on IIT Hyderabad. We basically have a largest demonstration of the use of self-consolidating concrete in producing form-free construction. So, in producing plaster-free construction. So we have form-finished concrete. This concrete that is used the way it looks when you remove the formwork. If done right, it has a beautiful finish. You do not need plastering, and it's an everlasting surface. But to do that, we have to engineer the material, get it to flow like water. So this is the self-compacting concrete that was used in construction of IIT Hyderabad campus. So you see the material flows like water. It essentially flows very freely, and it fills the formwork without the need for vibration. So you see, this is the concrete flowing under its own weight. So this is now very much possible. What I'm showing you is a video that is 7 to 8 years old. Now commercially SEC is available, it can be ordered, and we can start making structures with this material which are much faster to build. We've also made self-leveling geocrete. This is the fly ash based material we developed. We're able to make material which basically flows under its own weight and gives you the self-compacting aspects. Now coming to the final part of my presentation, which deals with 3D printing. So now the whole point is that when I make these rectangular beams, the central part of the beam is not very effective. It doesn't contribute much. It is the flanges, the ends of the beam, which are farthest away from the neutral axis, or the center part of the beam, which are most effective in carrying the load. The middle part only adds to weight. It doesn't give me too much, it doesn't contribute too much to the resistance. So in steel structures, I'm able to produce I sections, whereas in concrete, unless it is precast, I'm not able to do so. But what if I could do this through a printing process where I could do this on site? So, but to do that, I need to understand how to produce a material and what are the requirements. Now, simplest way for me to explain the requirements of 3D printing is through this example of a toothpaste. Now, if we understand our toothpaste, we know exactly what we need for 3D printing. If you look at a toothpaste, when I squeeze the tube, the material flows out in the form as long as I keep the pressure on the tube. Now, the material that is coming out of the tube comes out and keeps the shape of the tube. So if the tube is circular, what comes out of the tube basically has exactly the shape of the tube. Now, what is interesting is that the minute we let go of the pressure, the whatever comes out as an extrudate keeps its shape. It basically retains the shape on the brush. So basically, that's exactly what I need to engineer. I need to engineer a material which is concrete, which when I press on it or when I push it, it should flow. It should flow through a nozzle. As it's flowing through the nozzle and as it comes out of the nozzle, it should keep the shape of the nozzle. And if I basically want to build on top of it, as I add another layer, it should basically build up strength and stiffness sufficiently so that I'm able to add more layers onto that. So this toothpaste chemistry is what we are after in trying to develop mixtures of concrete or develop concrete mixes which can be used in extrusion based 3D printing. So there we have to pay a lot of attention to a lot of these parameters. Fundamental issues that we need to address are rheological aspects of viscosity, and with that we are now play viscosity and basically there are other properties called thixotropy and yield stress. So these are the three fundamental rheological parameters that we have to engineer. These are done using concepts of packing. So one has to look at packing of the material and using additives into the material, which allow me to engineer these three properties so that I can get a mix which is pumpable. I should be able to pump the whole mix. It should have non-segregated flow, which means concrete is a very inhomogeneous material. I have aggregate, I have paste, I have water. As I pressurize it and as I'm pumping it, water and the aggregate and the cement paste should not separate out. It should flow as one non-segregated mix. Then as it comes out through a nozzle, it should keep the shape of the nozzle. That is the shape retention part. And then buildability. So once I've extruded one layer, I should be able to add on another layer, which means the layer which is at the bottom should be able to take the layer of the weight of the layer which is coming on top. So whatever layer I've already extruded, once it's extruded, should internally start building up a structure so that it can take on the weight of additional layers. So all of this requires a lot of engineering. We have to control the rheology. We have to control the property development because while I want buildability, that is the structure should build up, it should not set. If it starts setting, then it will start setting in the barrel. So basically it should flow while it's in the barrel. It should only start developing this setting kind of behavior once it's out in the air. So that's a very fine balance that we need to achieve. And hopefully this video works. I can show you what 3D printing, what it is that we're looking at. So you see here a structure. This is basically the structure that was built when our Prime Minister Modi visited Singapore. This was a demonstration structure that was extruded layer by layer. And you see this is a layer by layer deposition. So multiple layers are deposited. So while the top layers are being deposited, the bottom layers have already hardened. So this is the entire form-free construction. And using this now, I'm no longer constrained only to rectangular shapes. Now, one of the biggest challenges with 3D printing, of course, is inserting reinforcement. How do I put steel reinforcement in there? So there's a lot of research. There's a very active area of research is how to work with steel reinforcement. Different ideas are being tried or are being tried. One of the most prominent ideas, of course, is the use of fiber reinforcement. Now, why not use these discrete fibers which get mixed into the concrete? And the advantage I gain with this discrete fiber reinforcement is I can place the precise amount of fiber reinforcement at the precise location where I need it, rather than putting a steel reinforcement bar, which sometimes is put even in places where it's not needed because I cannot abruptly cut it. With steel fiber reinforcement or fiber reinforcement, I can now precisely place it where it's exactly needed. And I can basically start getting into fiber reinforced 3D printed structures. So the final thing that we're looking at with the cement and concrete technology is to bring in nanotechnology now. So there's a lot of talk about use of nanotechnology, and we've already seen some examples of that nanotechnology use was in ultra high performance concrete, where a lot of nano additives are used there for strength. So that's already been done. But we're talking about other applications as well. The use of nanotechnology is also, nano additives are also being done for rheology control. A lot of the 3D printing applications use clay, nano clays, for getting that precise control of shape and extrudability and buildability. Now, the other applications we're looking at are self-sterilization, internal self-repair of concrete. So basically, nano additives like titanium dioxide have a photocatalytic effect, which can be used for scrubbing NOx from the atmosphere, and it's already become reality. Cements are available with titanium dioxide nano infusion in them. So, with the use of nanotechnology now and the looking at the material science aspects of cement and concrete now, basically we are looking to open up the paradigm and looking at the field and looking at it more from a science point of view, and bringing in opportunities from fields like ceramics, high strength composites, and electronic applications, and making this a truly high tech material. And the whole point is basically that we elevate the status of Portland cement to a high-tech material. And what you see as what I've shown on the lighter side, on the right-hand side, is someday maybe we'll take it to the moon and beyond. So how far is it possible? Well, I just want to leave you with this final slide here, where this is a photograph of a car which is made of material which is cement cross-linked with polymer. It's a MDF, that goes by the name MDF, macro defect-free cement. It is basically 95% by weight cement, cross-linked with polymers, and this material can achieve tensile strength of 200 MPa. So it's a really wonderful material. This is an actual car. The chassis, the body of the car was built of this cement material. This is used, this is raced across the continent of Australia. There's a race where cars are powered, solar powered cars are raced across the continent. So one particular year, this particular car made with a body of made of cement competed. It did complete the race. I wouldn't say it came first, but this is certainly possible where we can now start looking at it as a high-tech material. So with that, I think I've used up my time. I probably exhausted your patience as well. But I'd like to thank you for your attention and open the floor for questions. So thank you.
Thank you, Professor Subramaniam. In fact, it was very, very excellent talk. We got to learn so many things. Very nicely presented by you. So thank you so much. And all these appreciation in the chat box, if you can scan through, coming your way from the participants, and they're all very appreciative of your talk. So thank you so much for this wonderful session.
Sure. Thank you very much. I do have my email listed there. So any of you who want to contact me can drop me an email. Yeah. I would be happy to chat.
Yeah, thank you, sir. Yeah, any of the participants, in case you're willing to maybe get in touch with Professor Subramaniam for your research or anything of that kind. So he'll be really very willing to respond to you. You can maybe write a mail to sir. And thank you so much for your great appreciation to the speaker. I'm really happy with that. And in fact, as I promised in the very start of the session, that you will find this session really very informative, and that's what it is. I can see through your expression of appreciation. So thank you so much. In case you have some questions, maybe Professor Subramaniam, we can take some 2-3 questions. That's okay?
Absolutely, yeah.
Yeah, hello. Hello.
Yes, please.
Yeah.
Hello. Good morning, sir. This is Dr. Bhatia from the Jaipur. Yeah, thank you. First of all, I'd like to thank you. Thank you for your valuable, informative lecture and really very worthwhile. Thank you once again. And I have a little bit queries, and maybe it's a question. The first I would like to ask that what is the effect of the carbon nanotubes on concrete strength? In the last slide, you have told nanotechnology.
Yes. So there are different nano particles and reinforcement forms that are being used in cements. Yeah. Now, carbon nanotubes have been used in cement paste, where one of the issues with carbon nanotube is the dispersion. So once you disperse it properly, one has to use, because what happens is the carbon nanotubes actually tend to stick together. They have to be dispersed through ultrasonication. If you disperse them in the cement paste system. What has been shown is that the modulus of elasticity can be increased by an order of magnitude. So you start producing material which is much, much stiffer than your normal cement paste. So the whole point is that while with the use of carbon nanotubes, I may not gain much in strength, but I'm able to gain in stiffness. The advantage of this, and where a lot of people are looking at it as a material now in terms of stiffness, is when I have a high-rise building, stiffness plays a very important role in the stiffness. The stiffness of the material plays a very important role in the stiffness of the structure. Now, typically steel was preferred because it's a stiffer material, so I use less of it. Now, if I can produce the same level of stiffness in cement paste with the use of nanotubes, I use much less material. So that is the whole point. And that's one of those areas that's actively being looked at is basically stiffness enhancement with carbon nanotubes.
One more question, if you have time, then.
Sure.
And what is the best adhesive polymeric material for the concrete, sir?
Best adhesive polymeric material?
Yeah.
Depends on the application. I mean, if you are talking about repair type application where we're looking at sealing, then you have a set of epoxies or a set of organic compounds that are available. The requirement there is a low viscosity because it has to be able to penetrate through the crack.
Yeah.
And those are available. So that's one application. The other application that you would need epoxies or adhesives is for strengthening applications.
Yes.
Now, strengthening applications, there are usually we use two-part epoxies, which give you good bond with concrete. So it depends on the application that you're looking at.
Okay. Thank you. I have a lot of questions, but I'll give the time other the student. Thank you.
Sure. Thank you for your questions.
Okay.
Hello.
Yes, please.
Yes, may I ask question?
Yeah, please.
What about
Yes.
the sustainability case? So we can use different waste materials, and that can correlates with the cement structure.
Yeah.
Calcium aluminosilicates.
Yeah.
So what are the role of those waste material
Okay.
in the context of concrete? What are the different constituents? We have to use the aluminum oxide, the silicon oxide, whatever the calcium oxide is substituted with magnesium as well as different polymers. So how we can use different waste materials, including the marble waste, the calcium carbon.
Yes.
So how these get the sustainability?
Now, the whole point is this definition of sustainability. What do we call sustainable? So the first step in achieving sustainability would be to create less of an environmental impact. Now, of course, ideally, to be perfectly sustainable, my environmental impact should be neutral. In other words, whatever I take, I refill. So that's ideally sustainable. Now, but I think that's the ideal goal. But most of us, I think, at this point of time, have come to the realization that that is difficult to do. So let's at least look at something that minimizes the impact on the environment. And the way we assess them, the impact would be in different ways. One would be we look at the carbon, the other is energy, the third would be material usage. So, and there are other aspects also that can come into being. And we have to look at it from a life cycle perspective. Is I build a structure, what is the impact of this structure in terms of energy, not just the embodied energy, but also the energy that goes into the operational cost or the operation of the building or the structure. And then what is its long-term impact in terms of, suppose I build a structure for 50 years, then when I have to dismantle it, what is the environmental cost of the dismantling, etc. And then look at it in the total perspective. So the framework for evaluating the sustainability itself is kind of still, I think, not very clear to a lot of people, and it's still developing. So what we are right now trying to do when we're talking about sustainability goals, at least in construction, is to try and minimize the carbon footprint, try and minimize the energy, whether it's embodied or operational, and try and reduce the material usage. So a lot of people are working on different fronts, and because we have a material in cement, which is by its nature energy intensive, it needs a lot of energy to make. 2, it has a large carbon footprint. 3, in terms of volume usage, it is huge. So I need to kind of look at ways that I can then start substituting. So that's these are the 3 goals that we are broadly shooting at when it comes to trying to get sustainability into construction using concrete. So there, then anything I can do to remove cement from or replace cement helps. Now, marble dust is one of those examples that you've taken. Certainly, it contains calcium, which can be used, and it's being used. In fact, now, oftentimes what happens is when we do all these things, we have to look at one, it becomes region specific. So, marble dust is available in plenty in areas of Rajasthan where marble is mined, it's processed, it's cut, etc. But it's not available pan India, so or globally. So a lot of times what happens is that these, whatever we look at as a solution, can be sustainable locally. Because if I now look at the marble dust and try to move it to southern part of India, I pay transportation cost. I basically burn a lot of diesel in trying to move it, etc. So I may have to look for a local solution. And the local solutions may actually work wonderfully. And marble dust is being used as a replacement for sand. And sand is another material that is being fast disappearing from the planet because we're using it up in construction. So it is being used as a replacement for sand. It is being used as a filler material in concrete. So it is being done. So that's the specific example of marble dust in that region. Now, coming to the chemistry part of it, we have traditionally been locked into calcium-based cements. That's how it's come about. That's the history of cement. That's how cements are made. So now we are looking at alternate reaction pathways. We are looking at alternate chemistry. We are looking at magnesium-based cements. We are looking at aluminum-based cements. We are looking at alternate sourcing, alternate chemistry, which basically gets us away from this calcium forms. Or even if we have to use a calcium form, it should be of a form that can be done by mimicking nature, like what I showed you in the slide, biomimicry, where we're trying to produce it through a process which is basically mimicking what nature does, so that it is not too harmful to the environment, does not have a high carbon footprint, or doesn't require too much energy. So that's the thing. And there's also a lot of work being done on carbon sequestration. So why not have cements that can sequester carbon? So that's an alternate form that's being used. So net, basically what is happening is that we're looking at a lot of waste products. It just so happens that a lot of waste products of other industry have the desired chemistry that we want, or they have calcium and silica and alumina. So we're starting to look at these as basic materials for making these cements. And that's basically the entire line of research that is being tackled.
Okay. Okay, thanks. But one of the problem of sand, how the problem of sand,
sure,
sand substituent, whatever the manufactured sand, whatever the so how these sand, the problem with sand.
That's actually a very nice, very interesting problem. Southern part of India, sand is virtually non-existent. We don't have sand in the southern part of India because of over mining. We've basically done so much ecological damage that governments have put a ban on the use of sand. So we are using already manufactured sand, which is basically the residue that you get from coarse aggregate manufacture. So when you crush the coarse aggregate, whatever is the finer residue, which used to be thrown away previously, is now being used as aggregate. So across the entire southern belt, the peninsular India now, mostly we are using this so-called manufactured sand or crushed aggregate as our sand. Now, even that perhaps we have to look for alternates there too, because the aggregate are also going to, or the source of rock is also slowly disappearing. So now alternate aggregates are being looked at, and these alternate aggregates include manufactured aggregates. So these are aggregates that are made with fly ash. Sintered fly ash aggregate are now coming into use. So similarly, other manufactured aggregates are also slowly finding their way into use, because we, at some point of time, have to look for alternates to natural stone as aggregate. The third form which is being actively looked at is construction waste. The recycled concrete that you get from crushing of old structures, that itself is now being actively used, and its use is now permitted in regular construction up to a certain percentage. So these are all things that are now coming up basically because we are running out of natural resources.
Thank you. Thank you. Yeah. Thank you, Professor Subramaniam. I think, Dr. Chief answered. Yeah. Any other question maybe?
Yes, sir.
And then
Sir, this is
we'll,
Dr. Swati from
thank the
VIT
speaker and
Sindri.
conclude this. Yes, please.
Yes, sir. This is Dr. Swati from VIT Sindri. I also have one question to put on. First of all, sir, I would like to thank you for such an informative session. It was indeed very much valuable for all of us. And during the presentation, I saw that different aspects of fly ash have been covered for sustainable construction. So I basically had a question that fly ash is also utilized for extraction of rare earth elements.
Yes.
So I just wanted to know your opinion regarding the potential of the fly ash from the power plants out there in India. Is it having the potential to extract rare earth elements?
It's this is one of those things one has to be careful about, because the rare earths are there, but they are in very small quantities. Most of the fly ashes that we sampled across India, the rare earths, we didn't find rare earths in significant quantities. In fact, they were hardly ever present. So the only thing that is worthwhile is sometimes fly ash contains rutile. Rutile is titanium dioxide, some form of titanium. So that's one element that perhaps can be looked at in terms of extraction. Now, whether it's commercially viable or not, that is something that has to be looked at. Because when we're talking about extracting it, we're talking energy. I mean, fly ash is already a spent material. We'll have to put some energy to extract whatever you want to do. And when you're doing a comparison,
I hope Dr. Swati, you stand answered, right?
Yes, sir, absolutely. Thank you.
Yeah. Thank you. In fact, thank you. And in fact, like Professor Subramaniam, you explained, entire concept using beautiful illustrations and the videos as well. So that added colors to, in fact, your presentation. It was really very nice. And even though I'm not exactly from this domain at all, but even I could appreciate whatever you discussed today. So all participants, they have got benefited. That's what I can, I can understand out of their feedbacks coming in the chat box that I was scanning through. So really wonderful and really, very good talk, in fact. So thank you so much, Professor Subramaniam.
Thank you very much. Thank you all for your attention. And if you have any questions, please don't hesitate to drop an email to me.
Yes. Yeah. Thank you. And may I now request Professor Jakar G.C. Bikane to please conclude the session and express his opinion towards the end of the session. Dr. Jakar, please.
Thank you, sir. Thank you. On behalf of organizer, I would thank Professor Subramaniam for your very nice, very informative, excellent lecture, sir. And I think all have enjoyed your lecture, sir, and all have given their very nice and good appreciation for your lecture. So thank you so much, Professor Subramaniam, for giving this very wonderful lecture, and thanks to all participants for your nice interaction and patience. So thank you very much once again, all participants, and Professor Subramaniam for your very wonderful lecture. Thank you. Over to Professor Sathan.
Okay, thank you, Dr. Jakar, and thanks to all the participants, and most of all, thanks to the honorable speaker, Dr. Subramaniam. Thank you so very much, sir. And I think over to you, Ravi. You maybe now you can maybe close the session. And Professor Subramaniam, I'll share a document with you. Do the needful, share it back to us, right, sir?
Sure.
Thank you so much, sir. Thank you.
Okay. Thank you.
Okay. Thank you, and thanks all.
Thank you, sir. Thank you.